Yeah, so our next speaker is Larry Lapidez from Synopsys, where he's an executive director of business development at Synopsys, responsible for the Impress branded products. Prior to Synopsys' acquisition of Impress Software Limited in 2023, Larry was VP of Worldwide Sales and Marketing and a member of the founding team. Before Impress, he's held several roles in sales and marketing, including VP of Worldwide Sales during the run-up to the Vericity's IPO. I remember working with Larry quite closely. Larry holds a BA in physics with general distinction in physics from the University of California, Berkeley, an MS in applied and engineering physics from Cornell University, and an MBA from Clark University. He's obviously a busy man. And the talk today is a holistic approach to RISC-V processor verification.
Thanks, Mike. Much appreciate the introduction. Hello, everyone. Just a warning before we get started here. For the past 25 years, I've been in verification, hardware verification, software verification. But the key is I've been focused on simulator-based verification. But now I joined Synopsys 9 months ago, and Synopsys has a range of tools. I'm going to talk about a holistic approach to processor verification. For the first time in 25 years, I'm going to talk about formal verification as a real alternative here. And so the world might end, but we're going to try and get through it today. So I'm going to talk about RISC-V, maybe provide a different perspective than the other speakers so far today. Why should we use RISC-V? The challenges of RISC-V verification, echoing some of what Adnan had to say before, and then go through processor verification solution, the dynamic side of it, the formal side of it, and get through this. So why should we use RISC-V? So we've been talking about RISC-V a lot today, but why should we use it? Anyone can design their own processor based on the RISC-V ISA. It's an open standard. It's modular. So you've got a choice of which features to include or to exclude. It's extensible. The key is, with all this flexibility, you can design your own domain-specific processor. RISC-V is crossing the chasm right now. For some of us that have been around for a few years, we've seen this before in EDA. Actually, Mike mentioned Vericity, and this was a crossing the chasm moment in verification when Vericity and that style of constrained random verification driven by functional coverage was broadly adopted. And so we see here with RISC-V, it was initially only used by visionaries like Sci5, Andes, NVIDIA, Microchip. But then systems companies wanting domain-specific processors have come into this. Meta infrastructure, Google, IoT companies, early adopter companies, and we've seen this crossing the chasm. So now we have these early adopter companies that are coming in. And that actually changes the verification view here. Because now with early adopter companies, we need to provide easier to use solutions, because it's not just a handful of people using RISC-V, it is everyone using RISC-V right now. If we look at this now, then every semiconductor vendor has a RISC-V project in flight. Every hyperscaler company, Google, Meta, Amazon, et cetera, has a RISC-V project, at least at the test chip phase. Every automotive OEM in Tier 1 has a RISC-V project, at least at the test chip phase. We're into the mainstream here. We're crossing the chasm. So that's what's going on. And if we actually look at the expected market growth in RISC-V, it's huge. It's really significant here. And so as we talk about RISC-V verification, as Mike has talked about it with open hardware and from Tenstorrent and from Brecker and Synopsys, this is a significant problem because all these companies are adopting RISC-V. It's not necessarily replacing ARM or x86, but everyone is adopting it and everyone's adding some customization to it because that's the reason for adopting it. And so verification becomes a significant problem. And Adnan showed this a little bit differently, but 10 to the 15th verification cycles for an ARM application processor. What that equates to is 10,000 simulators running 24/7 for a year. That's a lot of verification going on. So the core user, the RISC-V core user, expects this sort of quality from their RISC-V core. The RISC-V core developer doesn't necessarily have those resources that ARM has. So how do you do RISC-V verification in a smarter way? And so that's what we're talking about here. We're talking about these challenges. Adnan had a great slide talking about design complexity and going up from sort of the basic instructions all the way to multi-core and cluster. And certainly you've got that. You've got the source of the processor IP, whether you're licensing it or getting it from open source or building it in-house. You've got the different use cases, and use cases make a difference because, for example, if you're building a microcontroller that only your company is building software for, that's going to be very different than a general purpose application processor that your customers are going to load software on. There's the processor verification methodology throughout the project lifecycle. What are you doing at the very beginning, at unit level verification, at processor level verification, at processing subsystem, at SoC? What happens when you get silicon back? Is there more verification to be done? There's the question of team experience, because this has been done mostly in ARM and Intel, AMD for the past 40 years. So do we have people with processor verification experience in the team? What's the productivity we're getting? What tools are we using? So there's actually a lot to go through here. It feels a little bit like Sisyphus pushing the rock up the hill, only to have it roll back down again. And but there are a number of challenges here. So Mike mentioned that I was with Empiris before. Empiris got acquired by Synopsys. I've been involved in RISC-V for about 7.5 years right now. So what have we learned in this time? What we've learned is sort of the obvious thing. Of course, a verification plan is needed. You can't just sort of go into this in a random way, and you need to address the key axes of processor verification: the single core methodology, the multi-core processor complexities, and the project life cycle. Also, you need to recognize that processor verification is different than SoC verification. The state space that you have in a processor is just way beyond what you're seeing in an SoC. You have to treat this differently. And as such, a high quality, fully functional reference model is needed. But as with an SoC DV, a full range of verification technologies is needed: dynamic, formal, and even hardware-assisted verification. So this is a very loose chart on verification process, verification methodology, but looking at this from unit where actually formal verification is quite good, architecture to custom instructions and CSRs to the processing subsystem. There are different tools that are going to have a different impact on verification and going to be useful at different times in the project. At Synopsys, we've got a range of verification solutions. This gives you an idea of what's going on here. There's a bit of a light there. So the formal verification solutions, including both property checking as well as equivalence checking. And then on the dynamic side, the key things that we'll talk about today are the Empiris DV solution, Sting for test generation, and won't really get into the platforms, whether it's simulation or hardware assist, but that's an important part of it too. But a key thing as well is here on the bottom, the Verde verification planning and functional coverage platform helps you actually bring these things together. So let's start with dynamic verification. This is the Empirus DV solution. It starts with the Empirus FPM RISC-V processor model. Again, Mike mentioned this in his open hardware talk. It's a commercially supported, commercially available reference model supporting the full RISC-V specification. Adnan, there's something like 148, I believe, ratified extensions right now. It's a little bit more than 100. So you've got to be able to support all that. You've got to be able to support it actually on which version of each specification, because one of your projects is going to use the 1.0 vector spec, one's going to use the 1.1 vector spec or something similar to that. Around that reference model, you're going to need to have that whole infrastructure to be able to control the comparison, to be able to handle asynchronous events, resynchronize the co-simulation that you're doing. You're going to need to have your checking, you need your comparison, and then you also need functional coverage. All those things are in there in that co-simulation environment. I'm showing it here with Synopsys VCS because I am working for Synopsys, but actually any system Verilog simulator will work just fine. And then the last piece of this are the tests. I've shown here with the Empirus TS test suites for specific complex features like vectors and PMP and MMU. And then the RISC-V ISA tests are actually a set of compliance tests that we provide at no charge as part of the solution. So that gives you an overview of what's going on there. I want to just spend a minute on the reference model here, because the reference model is a key piece of this. The architecture of this is that we've got this base model that supports the full specification. It's fully configurable, but then using the same APIs that are used to build the base model, we have an extension library structure that handles the custom instructions and CSRs. So actually, we don't even need to do this. Customers can modify the model themselves. They can maintain and support the model themselves. But because every RISC-V model that we build uses this base model, the base model has been used just a huge number of times. Let's go back here. So including users of both our commercial and free tools, there have been over 150 companies, organizations, universities that have used that base model. So it's actually pretty well exercised. On the functional coverage side, functional coverage is obviously a key metric here for verification. We've created a functional coverage generator to automate this so that you don't have to manually create your functional coverage, because manual creation can be well over 100,000 lines of code. That's tough to do without errors, and it's just tedious. So we automatically generate that and provide that. And we've provided some of the specs for this and some examples of the functional coverage on GitHub. There's the integration of Empirus DV with Verde. So I mentioned there that Verde is one of the things that brings dynamic and formal together. So actually, there's output from functional coverage data that gets reported in Verde, but also from that functional coverage and Empirus DV, you can output a CSV file or an MD file that can be integrated into your verification plan. So it provides a top-level view of what you're going to be doing. Recently, maybe 2 months ago now, Synopsys acquired a company called Valtrix. Valtrix had developed the Sting tool. It's a test generation tool focused on RISC-V. So it's got a number of different modes, generating constrained random, directed, graph-based tests, focused on verifying the RISC-V ISA custom extensions, multi-heart, memory coherency, concurrency. And then it's also focused on running on simulation, but also a number of users are running this on the hardware-assisted platforms on either emulation or on FPGA prototypes. And just taking a little bit more of a look at it, that top level there is some of the user inputs to Sting. There's a test generator engine, and then that exists as a library microkernel that's actually running on the device under test. Which gets me to the end of the world part of this talk, the formal verification. Formal verification, VC Formal, has been part of the Synopsys portfolio for a long time now. Formal is complementary to dynamic here in a number of different ways. But one of those ways is that it's doing a proof. It's not just looking at mismatches. Also, it's a white box verification technique. You need to understand your design. And on the one hand, it's got limits in terms of the size of the design to deal with, but that's also a benefit because you can do unit level, and designers can start with unit level verification. And so what we've done at Synopsys is focus on that unit level, focus on things like pipeline or floating point, load store unit, and then we've also developed a set of assertion IP for ISA verification. So this just gives you a little bit different look at that. On the right is that assertion IP, but there are also all these other applications in Formal that can be brought to bear on the RISC-V problem. And I'll just touch on one very briefly, which is the formal security verification. And I think the last speaker mentioned that something like 44% of designs now have safety critical pieces in them. Well, most every design has a security portion in it right now. And so being able to verify security and with RISC-V, that's a pretty important thing to do. So what have we learned in the last 7 years? Of course, a verification plan is needed. Processor verification is different than SoC verification, and a high quality, fully functional reference model is needed. And then also, as with SoC DV, the full range of verification technologies is needed. And the keys to success are support for the full RISC-V specification. Custom instructions need to be easily added and verified, and a silicon-proven processor verification tools, models, methodologies. That's what's needed. So thank you very much.
Okay, thank you, Alan. I probably don't have time for questions, so we'll move straight on. So thank you very much. Again, if there's any questions, you can grab Larry during the break after the next talk. There's a couple online which we'll email to you as well.
Thanks.
Okay, thank you.